So that was potassium's movement, kind of the first half of things. Let's talk about sodium's movement. And again, we're going to consider a hypothetical cell because we know our cells are not actually set up like this, right? There's more than one movement, more than one ion moving across our cell, but this second hypothetical cell is only permeable to sodium. And so again, reminding ourselves of the relative ion distribution here. Outside the cell, we've got sodium that's being balanced by the negative charge of chloride. And inside the cell, we talked about potassium being balanced by the organic anions that are inside the cell. So we're starting off again with the concentration gradient, or the chemical driving force is the first thing we look at in terms of the movement of this ion. So sodium has a chemical driving force into the cell because, again, we have that sodium-potassium pump that's pumping free sodium out. And so we have a higher sodium concentration outside the cell. So we've got a gradient now where sodium wants to diffuse back into the cell according to that concentration gradient. So we can see here that there's a chemical force trying to get sodium back into the cell according to its gradient. The second thing we now introduce is the electrical force. Okay, so as sodium is diffusing into the cell, the inside of the cell now becomes more positive, right? We've got more positive charge diffusing into the cell, creating this positive environment. And so we've got an electrical force that's trying to drag sodium in the opposite direction initially, okay? So because we now have a negative environment outside the cell, all this positive charge is now being dumped inside the cell, and the unopposed negative charge of chloride is now creating this negative environment outside the cell. So now we have an electrical force that wants to drag sodium back outside, so it's attracted to that negative environment outside the cell. And so sodium is going to move until it eventually gets to its equilibrium. And when it does arrive at its equilibrium potential, that value is positive 60 millivolts. So it's completely on the other end of the spectrum than potassium's equilibrium potential. We can see that it's, first of all, it's a positive value. And second of all, it's much further away than the resting membrane potential. We'll talk about how that becomes relevant in a little bit. But when sodium gets to its equilibrium, and so there's no longer any movement, the membrane potential at that time is positive 60 millivolts. So at this time, we have equal and opposite forces trying to move sodium. They're of the exact same magnitude, and so we have zero movement of sodium as both of those forces cancel out. And so to summarize here, we have a chemical movement of sodium into the cell that is opposed by an electrical movement of sodium out of the cell. And so the net electrochemical movement is initially into the cell because of a stronger chemical force, but the electrical force is going to continue to rise, and we're going to see how that kind of combats the chemical force. So what we see when we kind of put both of those ions moving, when we put those two things together, we see that there's a chemical force for potassium out of the cell, a chemical force for sodium into the cell. Again, this is purely owing to the concentration gradients of these ions. And then we add the electrical forces here. But the electrical forces gets a little bit more tricky, and I'll tell you why. If you recall that I mentioned that the membrane is more permeable to potassium, meaning that there are 25 times more potassium channels in the membrane than there are sodium channels, then that creates an environment where potassium is going to leave the cell more vigorously than sodium is going to enter the cell, okay? So there's more potassium leaving because potassium has more channels. And you can kind of think of this as more doors, right? More doorways or more passageways for potassium to leave. And so more of it is going to leave than sodium kind of all trying to rush through this one door, or there are less channels, let's say. There's less channels or less doorways or less opportunities for sodium to enter the cell. So more potassium leaves the cell. And so what we end up seeing is that the inside of the cell becomes more negative, okay? And now, since the inside of the cell is more negative because of that increased potassium leaving the cell, when we now begin to consider the electrical forces, they're going to be both trying to get back into the cell, right? Remember, they're both positively charged ions. And so now that the inside of the cell is more negatively charged, owed to the fact that we've got more potassium leaving, because potassium can leave the membrane more freely than sodium can enter the cell. And so now we see there's an electrical force for potassium trying to move it back into the cell. And there is also a an electrical force for sodium also trying to move it back into the cell. But even with that said, the speed or the magnitude or the rate at which these ions are moving differs again because of the differing overall electrochemical forces. So if we combine the electrical and chemical force for potassium, because they're now in opposite directions, this is going to be a smaller value. We're going to have to subtract the smaller force, which happens to be the electrical, from the chemical force. And so we're going to end up with a smaller value here in terms of the outflow of potassium. So potassium is going to basically be trickling out of the cell. It's going to be moving much slower out of the cell because it has an opposing electrical force that's trying to drag it back into the cell. Sodium, on the other hand, will not have that scenario. Sodium is going to be rushing into the cell because we have two forces for sodium trying to move it into the cell. We've got a strong chemical force into the cell. We've got a strong electrical force also into the cell. And we talked about what we do when we've got two forces in the same direction. We simply combine the value of those forces, and the overall electrochemical force will be in the direction of both those forces, which is inside the cell. So we're going to end up with a bigger value, a stronger magnitude of the electrochemical driving force for sodium, and a weaker magnitude for potassium. So we've got a outflow of potassium that's very slow, kind of trickling out of the cell, but we've got an inflow for sodium that's kind of just rushing in. Sodium really wants to get into the cell because of that combined, stronger inward electrochemical force. And so after all of the movement of both of these ions, so now we're looking at both of the ions moving according to their electrical and chemical gradients. And so now after all of the movement takes place and the ions get to steady state, this is where the influx and the outflux are balanced. That's what steady state means, where we no longer have a net flux in either direction, but the movement is kind of just being balanced out here. And when we do all of that and the cell gets to steady state, and if we stick a voltmeter into that cell, the reading that we get is -70 millivolts. So that is how we establish our resting membrane potential. Because of the relative concentration gradients of sodium and potassium, because of the relative permeability of sodium and potassium, right? The fact that potassium has a higher permeability, i.e. more potassium channels than sodium does. Because of those two factors, along with the sodium potassium pump that's kind of in the background, just pumping sodium out, pumping potassium in, because of those factors, we end up at this steady state where the membrane potential of the cell is -70 millivolts. And so we've got a more negative charge inside the cell and a more positive charge on the outside of that cell. Okay. Let me pause here and see what questions may have come up. So what questions do we have about that so far? So we talked about these two hypothetical cells, one only permeable to potassium, where we consider the electrical and chemical forces separately, and then we put them together. And then we think about a sodium hypothetical cell. And again, we look at the electrochemical forces and put them together. And then we put the whole thing together, which is the movement of both of these ions. And this is how we establish that -70 value. So someone is asking, is this continuously happen or is it a one-time thing? So this is always happening in the cell. And this is how we got to that place that the cell is at rest, okay? So this is always happening in the background, and we'll talk about how we maintain this. So cells maintain their resting memory potential by the presence of the sodium-potassium pump and the leak channels. And so once we set up the resting membrane potential, then the two pumps and the channels, the pump and the channel, sorry, are going to maintain this environment inside the cell. So this is essentially how we got to this place of -70. Okay. All right. I hope that made sense. I hope I answered that question carefully. I hope I clarified that. So basically, we're just looking at a hypothetical scenario that explains how we get to the -70, but what's always happening is the -70 is where the cell is at rest. So the events that we just talked about are only explaining how we got that -70, why we see that -70 at rest. What's happening inside the cell to bring us to that -70. All right, any other questions? Okay, let's see here. Okay, yeah, so someone's asking if potassium has the negative charge. It does not. Potassium is a positive charge, but that is being balanced out by the negative charge of the organic anions. And it's important to understand that both of those things are present inside the cell so that we can understand that when potassium leaves the cell, that's why we now have a negative environment, because of the remaining negative charge created by those organic anions inside the cell.